and we're doing a short segment here on interrupts and interrupt loading as it applies to delivered workload performance. And the reason we're doing a specific segment on this is because it does come up from time to time when we take a look at customer performance issues and the workloads they're running, especially these days in light of the very fast devices that you tend to find on modern systems today. 10 gigabit network cards, fiber channel HBAs that have multiple 2, 4, 8 gigabit ports are capable of actually moving a very, very large amount of data, generating a lot of I/O, and all of that I/O needs to be processed on the CPU side at some level, and a lot of that processing is done in interrupt context, where the HBA or the network device generates an interrupt to the CPU executes an interrupt thread to do work on behalf of the device, whether it's to process receive packets for network or FCAL packets for an HBA. So let's just spend just a quick minute on what happens on Oracle systems when they boot up. There's n number of I/O devices on n number of CPUs on a given system, and those devices bind their interrupts to CPUs in kind of a round-robin fashion. Now, just a quick note on x86. That round robining was fixed in Solaris 10 Update 8, so make sure you're on Solaris 10 Update 8 if you're on an x86 platform. But in general, the system attempts to do a nice even distribution of interrupts to CPUs such that no one CPU gets overwhelmed with handling interrupts and is capable of doing other work. And again, on x86, Solaris 10 Update 8 is very important for that.
So if I may, I guess the classes of problems that you're seeing are potentially, so I guess one would be the interrupt CPU becoming saturated.
Right.
And so, limiting your performance of a system even though maybe there's a lot of other CPUs available to run stuff.
That's problem A.
And the other would be around binding the fact that an interrupt is actually nailing down whatever was running on that CPU, which is not able to make further progress, which is a specific.
Right, that second problem is what you tend to run into, or what you could run into when a CPU is shared by both application threads and interrupt threads. And what happens in that scenario is when a CPU receives an interrupt, if it's actually running an application thread, it does what we call pins the thread, which, without getting into a lot of technical detail, it just kind of pushes it out the way. It allows the interrupt thread to run. When the interrupt thread is done, the interrupt thread comes off the CPU, the application thread is unpinned, and it's allowed to continue. And that's actually an optimization. It's an optimization. We don't incur the overhead of an entire context switch every time this happens, and that's generally a good thing. However, if the CPU is handling a very, very high rate of interrupts, right, so that means it's potentially pinning a lot of application threads, you have a couple scenarios that could happen here. If those application threads are, say, holding an Oracle latch or an Oracle semaphore or a workload latch, then all of that pinning could create a domino effect in terms of the throughput that the workload can get. And the second problem you can potentially run into is the interrupt thread stepping on the cache lines of the application thread, and it's dirtying the cache, and the application thread doesn't necessarily get the high hit rates that it should. So that was a very good categorization of the two issues. Issue A, again, not necessarily getting all the throughput you can out of your 10 gigabit NIC or what have you, because the CPU is throttled handling the interrupt load, or problem B, the sharing of CPUs by application threads and interrupt threads.
And would you say, you mentioned interrupts, the major kinds of interrupts come from networking and disks. Is it your observation that it is more network bound, which manipulate more small packets?
Yeah, absolutely. I mean, the vast majority tends to be network class interrupts versus...
Because those manipulate smaller packets, in general, and the I/O size are greater, so the amount of work done in the interrupt thread is proportional to packets, not the amount of data. So a big I/O or a small I/O is the same general amount of work to an interrupt thread.
Exactly right. Yeah. So it certainly falls more into the network class, much more so than
device.
Yeah.
And I think a reason for that would be for networking, like a 10 gigabit interface, you can do hundreds of thousands of packets a second, and unless you've configured it otherwise, each of those packets is an interrupt.
Yeah.
That's right. Yeah, every received packet is an
I
interrupt.
wouldn't say that actually. So there are coalescing that happens
Yeah.
in networking, quite a lot actually. So
That's why I said unless you've configured
Right.
well,
otherwise.
and I emphasize because by default it is configured. I wouldn't assume that the
Yeah.
number of packets is equal to the number of interrupts, and yeah, so that's an important distinction.
And
here.
the other important point to make is that, especially 10 gigabit NICs, but even some of the 1 gigabit NICs actually have multiple receive channels. So they're not like simple devices like years ago where they have one receive channel, they generate one interrupt to one CPU, and that's
because those
that.
were getting saturated.
Because they were getting saturated, so we needed to build devices that actually have multiple receive channels. They take advantage of the new, MSI X interrupts, the message signal interrupts now with the extended information that they can send to CPUs, and a single, say NXGE card, for example, or IXG card. IXGE card can actually have its interrupts bound to 2, 4, 8 CPUs if necessary.
Yeah.
So you get more CPUs handling that interrupt load, so you're able to to get to that wire speed of your NIC if your workload requires it.
So and so we were saying about network performance, about networking, which are by and large the one that generates a lot of interrupts load. But in Solaris today, right, we've got the networking stack as getting more intelligent. They're more dynamically trying to adjust the load between interrupts and let's say helper threads to handle the same network. So it's very complex today, to know whether the stuff is going to be done on networking or not, or if the networking stack is going to be handled by interrupts or not, and there aren't like.
That's a good point, Rock, and I should point out that there's some really good work going on in Solaris kernel engineering around setting the correct number of MSIX interrupts for the faster devices, and generally just trying to do more of the right thing out of the box, such that the need to take a look at this post production and actually make some changes will become less and less necessary over time.
Yeah, if you do 10 gig performance, for example, and you want to get the most out of it, interrupts are something that you're going to run into. Your card, by default, may already coalesce interrupts so that several are collected together before they'll interrupt the CPU. That's usually based on a time interval, so the card will wait a tiny amount of time so that it can aggregate a few together before spending that fixed CPU cost of making the interrupt call. Sometimes you might be tuning that to turn it on and off to see what difference that makes. You may be able to tune the coalescing interval, how long the card waits for aggregating together packets.
You're really trying to get multiple packets per interrupt in general.
In general, that's right.
It's a really big win.
And it's a trade-off between throughput and latency. If you make that interval too big,
yeah.
then small individual packets coming in can have
You
a
don't
high
want that.
latency. So that is
That's
something
even worse.
That is something worse.
It may be worse, depends on the workload, right?
And also check out DLADM, which is the new tool set for Solaris, which is part of Project Crossbow. And there are CPU bindings as a property, and that can also have an effect on interrupts. That's something that I've tuned in the past to get the most out of 10 gig performance.
But not in Solaris 10 yet.
You know?
Open Solaris right now.
Yeah.
Yeah, but yeah, it's a good point, thank you. Okay, so that's kind of the big picture on what happens with interrupts and why this is an important conversation. So the next thing to talk about then is the tools you use and kind of what to do about it. And the good news is that figuring out if this is a problem and figuring out if you need to do what we call interrupt fencing, which is to fence off CPUs to only handle interrupts such that they don't run your application threads, is really easy to do. And you could do it in a dynamic way such that you could do experimentation. Brendan and Rock talked about experimentation in another performance talk. And you could do all this while your production system is up and running and figure out if it makes things better or worse or no different, and then change things.
You're saying you can easily today move the interrupts, even the number of CPUs? Not necessarily targeting move, but you can do a redistribution of the interrupts? Is that what you just said?
Yeah, so by definition, there's no way in Solaris to say, I want this interface to interrupt the CPU. You can't do that.
Okay.
But if you change the state of the CPU in Solaris, if you put a CPU in no interrupt mode, which you can do dynamically with either PSR ADM or with PSR set if you're using processor sets, once you change the interrupt mode of one CPU, Solaris actually redistributes the whole enchilada. So they are
So you can
redistributed,
kick
yeah.
the whole thing and then.
You can give the whole thing a kick, right, and shuffle things around. And again, you can do all this dynamically. So if you were to, for example, turn interrupts off on a given CPU or a given group of CPUs, and things get worse, you can just turn them right back on again. And you do all this dynamically. You're not restarting your application.
But you're not guaranteed you're going to get the same distribution as before you kicked it the first.
No, you're
You
not.
kicked it twice.
Yeah, no, you're not. No, you're not. That's true. That much is true. So the tools in your toolbox for taking a look at this is MPStat. So MPStat gives you a row of data for every CPU on your machine, and it includes interrupt counts. So you have interrupts and interrupt test thread counts, and you also want to take a look at sys-time, because theoretically, if a CPU is handling a lot of interrupts and spending a lot of time in the kernel, so you would probably see CPU utilization in sys with a very, very high interrupt load. INTR-Stat is a dtrace-based tool that will give you statistics on interrupts per CPU. It'll tell you which devices are interrupting which CPUs, and how much time, what percentage of time the CPUs are spending in the interrupt handler, that's really what you want to know, right? Or my CPU is spending a lot of cycles in the interrupt handler. MDB has a D command called interrupts. So you can use that to get just a tabular picture of which devices have their interrupts bound to which CPUs. And then PSR ADM and PSR set are your two kind of CPU interrupt manipulation tools, where you're going to do things like tell CPUs, I don't want you to handle interrupts anymore, or fence interrupts off from your application workload. So probably the easiest way to do this is with PSR set. If you've looked at MPStat and INTR-Stat, if you suspect that you have a CPU that's spending a lot of its time handling interrupts and is pinning a lot of your workload threads, just use PSR set and put that CPU in a processor set. And that's actually all you have to do, because by definition, once you create a user-defined processor set, the Solaris kernel will not put any application threads there unless you bind threads there. So by virtue of the fact that you create the processor set with the CPU in it, and you don't put any application threads on it,
Okay.
you've essentially fenced off that CPU.
Okay.
Very, very easy. Things get worse, or it doesn't help, tear down the processor set. It's all dynamic, it's quick, it's easy, it's really nice to have that kind of flexibility to address the problem.
And so you can do this fairly blindly, so you just say, oh, this CPU, high interrupt count, high system time, I suspect there's a problem? Just do the preset?
Well, so
or do you target more?
It depends on to some extent, on how much time you want to spend doing analysis in terms of proving that you should do this versus just doing it and seeing if it makes things better, right? So between MPStat, INTR-Stat, and dtrace, which is also a tool you can use, you can figure out empirically how much time your CPUs are spending handling interrupts. Okay. And so you could choose to take the time to do that. Or you could simply say, well, I ran MPStat, and I can see that CPU number 8 is handling 225,000 interrupts per second. I don't want it running any of my application threads. I'm going to put CPU number 8 in a processor set with PSR set. That takes 5 seconds, and you can figure out, did your workload get better?
Yep.
Whatever. So it has to do with the knowledge level, the skill set of the person that's actually doing this. You can measure it empirically, you could do the experimentation, you can do both.
So one thing I learned from Paul Rietmüller, another great
performance engineer, great guy.
Should be here, is that if your CPU is like 50-60% in interrupt mode, okay, it's 40% user mode, and you think you might want to use this. But because interrupts are very small and come in and all the time, they perturb your cache a lot. So the 40% that you are given to user time is actually very unproductive use of that 40%, because you're coming back from an interrupt, the caches are dirty, you will not be getting a lot of work in that 40%.
Right.
So as soon, I don't know if you've got a rule of thumb like this, but as soon as you're 50-60% maybe consumed by interrupts, might as well just fence that CPU out. We've got a lot in general in our systems today.
Yeah, and that's another good point. And the other consideration is the type of system you're on too, right? So if you're on an x86 based system where you're dealing with CPUs that are running at 3 gigahertz plus clock speeds, they tend to be able to handle higher rates of interrupts before getting bogged down than, say, a T5240, a UltraSmart T2 Plus based system, where you have lots of threads and lots of cores, but the single core performance is something less than some of the other CPUs, where a core could get bogged down through a high rate of interrupts sooner than on, say...
so the T-shirt, but you have a lot of CPUs, so
But you have
fencing a few doesn't matter so much.
That's actually a great upside, yeah, because if you're on a CMT system, you have a lot more CPUs, you have a lot more flexibility in shuffling things around.
And do you fence out the whole core, or?
So that's a great question. Do you fence out all 8 threads associated with the core? And the answer is
It depends.
It depends, right? The answer is it depends.
For us, yeah, it's always it
Yeah,
depends.
so again, it's experimentation, use PSR set, try just putting, say, the 4 threads associated with the core and maybe add and subtract the other virtual CPUs associated with that core and see how things go. It depends on the device and, yeah, those types of things. Did we forget anything important? I don't think so. So essentially, just to summarize, on modern systems today using modern I/O devices, interrupt handling can become a significant amount of CPU processing, and the sharing of those CPUs with application threads can, in some cases, induce poor performance on the workload you're running. It's advantageous to be able to measure that, and you have the tools to measure that with MPStat, INTRStat, and dtrace. And it's also advantageous to be able to do what we call interrupt fencing and isolate, partition your application threads from those interrupt threads, which in some cases can give you overall better workload performance. And that's it. Thank you very much.